and welcome back to day 2 at the Johns Hopkins University Applied Physics Laboratories 2021 XR Symposium. Again, my name is Nick DeMatt, your host for this event. We hope you found day 1 interesting. As I mentioned yesterday, we're using ZoomGov, specifically their webinar format. And just like yesterday, we'll be showing a video recording of each presentation today. You know, the audience members, you may submit questions at any time during the presentation or at the end during the Q&A session of one of these presentations. This way, the presenter can answer questions in real time and provide some additional insight in a timely fashion. The attendees may also monitor the chat session to send questions to the event panelist as needed. If a session ends early, we will delay starting the next session until the posted agenda time. This way, everyone can continue to use the agenda to plan their schedule. The question about presentation copies came up several times yesterday. Unfortunately, we won't be providing a copy of any presentation either during the event or at a later time, but you may contact the presenter directly to see about obtaining a copy. The best way to do that is send a direct chat to them during the presentation to exchange contact information. But if you're unable to do that, you may send an email to the event contact, which is listed on the event website. We also have a change for tomorrow's agenda that I want to mention. This is due to a popular demand. We have added a talk titled CAD to Game Engine Pipeline. So, that should resonate with those of you who are trying to put in 3D mechanical CAD designs inside an experience, whether it's VR or AR, mixed reality, doesn't matter. And so this talk will highlight the steps that we take here that we believe are actually best practice steps that most people and everyone should be thinking about if they're interested in doing this type of XR work. So as such, we'll be going a little bit past 4 o'clock, even though that's what we had posted as our end time. So be on the alert. We'll put that new agenda up. It's already up on the website, but we'll also add it to our slides as we go through the day here. I want to once again mention our collaboration with Mr. John Grant in the Virtual Worlds Forum. Together, we're working to bring attention to the immersive technology work that we're both doing for the DoD and our other government agencies. The VWF, Virtual Worlds Forum, is a group of U.S. government representatives that are exploring, developing, testing, assessing, and using the new breed of extended reality. Pre-COVID-19, the forum met about every 3 to 4 months at various locations across the U.S. to collaborate to help reduce the individual organizational burden that many of the agencies were seeing. During the COVID-19 pandemic, though, VDF has been meeting virtually, just like this event, and they've been trying to meet about every 6 weeks. That event provides an opportunity for the government, academia, industry partners to discuss and experience various XR capabilities of interest. John will be our last presenter on Wednesday, and that's when he'll be giving a live tour of his Fort Huachuca facility and also providing an overview of Thursday's 20th Virtual Worlds Forum event, which will be hosted on Microsoft Teams. The theme for that event is head-mounted display ergonomics, covering such topics as safety, comfort, wearability, sickness, strain, eye strain, neck strain, things of that nature. You're encouraged to reach out directly to Mr. Grant via his email address to learn how to register for Thursday and to learn more about the forum in general. Today also, I want to take a few minutes to highlight, I would call it a publication that we did in November. APL has a long tradition. In fact, I think this is our 60th year of publishing our technical digest journal. And that journal is open to the public. Right? It's something that we do in the public domain. But for the first time in November, we published an issue of the journal that was dedicated solely to immersive technology. And if you see on the screen there's a URL, and somebody on the panel will post that into the chat session, that you can go directly, not just to see this issue, but any of the other issues in the history of the digest. This is an award-winning journal that our dedicated publications team here at APL has done a fantastic job with over the years. This particular issue, as I mentioned, is dedicated to XR, and there's a collection of about 16 articles in there that highlight some of the work that we've been doing over the last 5 years in the XR domain. There's also an article in there that gives you a little bit of insight of what we're doing and what our vision is and where we think we'd like to go with XR at APL and for our sponsors. So I encourage you to go to that site, take a look at it. As you see, there will be the articles cover such topics as intelligence and special ops, first responders. You see the list there on the screen. So it has a broad spectrum of use cases. Hopefully you'll find at least one that'll be of your interest. Also to this digest, for the first time in our history, is that we've included an interactive XR experience. And we're fairly excited about that. But it's not so much that the experience in itself provides a great deal of information. It's that this is the art of the possible, right? So when we think about how we might want to apply XR, both here at APL and again for our sponsors, we think about, how do we change how we communicate today? What are the different ways that we can reinvent, general procedures or practices that we've been doing forever? So if we can include XR experiences in a document, for instance, perhaps we do this in proposal work, or perhaps we do it in any other type of document that we deliver. Or if you want to go and evaluate technologies of WebXR, how do we engage even just within APL, how we want to communicate information across the Institute, whether this be through a general browser application or some other type of social media. So we hope that you'll take a few moments to go visit the website, try out the interactive experience. You can use any type of Android or iOS device. It should work, supporting for that. And again, we look forward to any feedback through that method. There's a way to respond to the digest team to share with your thoughts about this issue itself. So thank you. Okay. As a reminder for our APL and government attendees and the symposium today, please note that the presentations have been cleared for public distribution. However, any information about a particular project that would be considered CUI will need to be handled offline. Yesterday, I spoke of how fast change is occurring in the XR world. This is a challenge for all of us. At APL, we're standing up an XR team dedicated to making our XR journey one that enables our staff members to aptly apply this technology for their sponsor work and for our institution. APL attendees may reach out directly to me to learn more about our mission. On behalf of my fellow APL team members, I thank you for attending and sincerely hope that you will have a better understanding of how immersive technologies can be applied to benefit your team and your stakeholders. In the meantime, we're going to take a very short break right now, and Ari will be back to introduce our first presentation at 11:15. Thank you.
Hello, everyone, and welcome back. We'll be starting our first presentation of day 2 of the XR Symposium in just a moment. I'm Ari Rapkin-Blenkhorn. I'm a member of the XRCC, which is APL's XR Collaboration Center. This group was recently established to act as a hub for XR efforts across the lab, consolidating knowledge, advice, resources. We have a repo of models and software. We lend VR and AR headsets to teams around the lab. And in general, if you are considering using these technologies in your work, we'd love to hear from you. Now, moving on to our first presentation this morning, our speaker is Ian Hughes, who is from APL. If you were watching yesterday, you saw Ian and Brandon's presentation about the environmental navigator. Today, Ian will be talking about the spacecraft harness fabrication XR application that he's developed. Let's go to the video.
Hello, I'm Ian Hughes from the Johns Hopkins University Applied Physics Laboratory, and I'm the lead software developer on the Spacecraft Harness XR fabrication application. So the objective of this project was to explore a replacement for Vuforia Studio, which was being used to show a mixed reality visualization of spacecraft electrical harnesses for their fabrication. So while Vuforia Studio has improved this harness fabrication and requires no software development on our part, there were a number of limitations that we found with it, so we needed to explore an in-house application. Vuforia Studio was unable to deliver a HoloLens experience, and it only worked with tablets, so it was not hands-free. The model tracking tended to lag or drift, and it required the spacecraft or fixture to be in a specific orientation. So in other words, if the spacecraft was moved, the experience needed to be recreated. We were also unable to get the advanced 360 model targets to work with our models. So our in-house application overcomes most of these limitations, and we also decided to explore better model management between our PLM system and making an XR experience. So the in-house application followed the approach shown here. I'm going to go into more details on each of these steps in this presentation. First, we take exported CAD models of the spacecraft or fixture and the harness, which are very large. Usually they were exported in a step file format. These are then reduced and converted into a 3D model for a game engine. We used Unity for this application. We manually generated a text file that describes how we were going to use the models in the XR experience. And then we import the model into Unity, and a script combines the models and the information in the text file to create a prefab for the mixed reality visualization. So a prefab is a collection of objects and scripts and other components. So this is the container that holds all the pieces needed to create the experience we want for the set of models. Finally, we have a HoloLens application that was developed to load these prefabs, align them to the real spacecraft or fixture, and then place the AR visualization of the harness on top of the real object, giving us a mixed reality experience. This was a quick prototype effort for Europa Clipper. We did have a schedule slip of about 5 months from our original target due to the pandemic starting out right about when we wanted to test the final application in the clean room. Okay, so the way this application works is you need a pair of CAD models. The spacecraft or fixture model is the real-world object that you want to place an augmented reality harness model onto. It is there for the alignment of that object as well as occlusion culling. And occlusion culling means that you're using the model to block the rendering of parts of the harness model so that you're not able to see those parts because the real world object is in the way. The harness model is the AR object that you want to display on top of the real spacecraft or fixture. This is the object that is being assembled So the AR visualization is used to guide that fabrication or assembly. So for this demonstration, we use the Europa Clipper propulsion module and its electrical harness. These models by themselves could never be displayed in the HoloLens as they were quite large, a combined 25 million triangles total, in fact. The HoloLens 1 is only able to display a few million triangles, and preferably much less for the best performance. Given the size of these CAD models, we discovered that it was not very easy or quick to get them into the HoloLens. So a large part of this project was spent coming up with how we would automate the management of the CAD model to XR experience, so that we could iterate very quickly through a series of tests, or for future projects, we can make it easier to repeat the steps that we followed for another pair of models. So this diagram shows the flow that we followed. Some of the parts of this process were automated that are shown in green, and the steps in blue are manual. Our CAD models that we used in the prototype were from different CAD programs. So part of this model management was making sure that the exports matched in scale, rotation, and origin. So first the models were exported from their native applications as step files, and then made available for the automated steps that I will go into detail next. So the exported models were decimated and converted in Pixie Studio. Pixie Studio is a software application that is designed to work with CAD models and prepare them for use in a game engine. It has a scripting interface that uses Python. So for this step, we used a script to complete the conversion automatically. The 25 million triangles that I mentioned earlier was reduced to 500,000 or less. And we did a couple different levels of detail in Pixie Studios, so the output varied a bit for each of our tests. I show here an example of some of the steps that the script goes through in the model imports in the center of this slide. The JSON file that we created is the text file that we wrote manually for the Unity import. The purpose of this file is to tell Unity how to package the pair of models. So this includes the coordinates of the alignment points, and I'll explain what those are in a moment. There's also a scale factor and a rotation vector, and also the name of the other model in the pair. So the fixture model would refer to the harness model to be used, and vice versa. The scale and rotation are important because, as I mentioned earlier, the models were exported from different CAD programs. So even in this case, the two models did not share the same axes or use the same units. So this data is used to make sure everybody gets along in the final output. So the Unity editor script is where a lot of the magic happens for the application. So it turns out that decimation from 25 million triangles to 500,000 is actually not even enough for the HoloLens. These large CAD models have tens of thousands of tiny parts that get imported into Unity as separate game objects, which means they all have separate meshes. Even if these meshes don't have very many triangles on them, they can have 5 to 10 triangles. Having tens of thousands of objects to render makes the graphics card make what's called a draw call for each one of those. The iteration of this draw call loop is very expensive for the graphics driver, so it's better to have one large mesh with all of the triangles instead of many thousands of tinier meshes with less triangles. So where I could, I combined the meshes into the smallest number of game objects, and that's primarily what this script did. I was able to do this and still maintain the texture information, which means that all of the colors that were in the original CAD data were maintained, even when combining all the meshes. For the harness, however, we wanted to maintain some of the hierarchy for the visualizations. So the meshes were only combined by the first major part number under the top level for the harness, instead of trying to get the fewest number of objects. We did this so that we could get the harness parts could be shown or hidden based on the hierarchy, and I'll talk about this more later. And then the script also got all the models lined up and set up for occlusion culling and the alignment procedure, and attached all the model behavior scripts for data handling in the HoloLens app that were needed. Okay, so I've been discussing about these 3 alignment points several times throughout this presentation. And the reason for these special points is for our targeting method. So I credit Boeing Bark for coming up with this method, or helping us come up with this method, because they had a similar method in their product. We did develop this targeting method from scratch on our own, but we based it on descriptions of Boeing Bark from their presentations given on the topic. So the 3 points that I've been referring to are points on the real-world object that the user can touch with this 3D printed alignment tool that's shown in the photo. This tool has an image target on it, and the HoloLens application knows where the touch point on the back of the tool is, that point that's shown on the left side of the image. It knows where it is in relation to the image target. So when the HoloLens cameras see the image target, we can transfer a real-world point to the augmented reality space. And by transferring 3 specific points, we can then transform real space into augmented reality space, which allows us to have a mixed reality experience, and the AR visualizations can be placed directly on top of the real object. We also had it hold an Xbox controller. That's what the clip at the bottom is for. And this allowed the application to be controlled using that instead of our voice or air taps. Okay, so this animation here shows how this tool is used. This is a very early version of the application. And because of the pandemic, I was doing a lot of the development at home. So I actually used the tool with my car as the quote-unquote spacecraft. And I used a model of the DeLorean time machine as the harness. So we actually purchased the model of my car for this project, and I got a free model of the DeLorean time machine, and then I sort of combined them in order to align the model, align the model of my car with the AR car with the real car. So you'll see here that after I select the 3rd point, the car model with the DeLorean harness appears. And I was able to make the car model disappear so that I could see just the harness part, which was the DeLorean harness on my car. So the procedure here is that the user knows where the 3 touch points are. They're predefined in this particular case, and the user places the tool at each of those points and then captures them with the HoloLens seeing the image target. And then the experience begins after all 3 points are captured. The application I developed was very much a prototype. It wasn't really intended for production use. It was designed to do the performance testing that on various decimations from Pixies or outputs from the CAD that we were trying to look at in this project. So it didn't have any way to connect to a server or load a live model, although we would probably want that feature in a production application. So we built the application with all of the models already loaded in the application as objects. It did have a series of menus that made it easy to choose the model and then either place it near an image target, near the image target that was on the tool, or use the tool with the 3-point method that I just described. So we did a series of tests on the HoloLens 1 to try to figure out what the limitations were for the size of the models that we could display. We measured the performance in how many frames per second or FPS that the HoloLens could run at when looking directly at the model. So in particular, Vuforia Studio was not able to create a HoloLens experience with the set of models that we were using. So this is why this was an area that we spent a lot of time on in order to find out why. We needed to really find out what the limitations were and how much we needed to decimate and combine the meshes in order to produce an experience that was usable. So obviously the direct exports were much too large to be shown in the HoloLens, but most of the various Pixie decimations that we did all performed about approximately the same. So it didn't really matter as long as the number of triangles were down below 1 million. We did learn that the best experience was had when only part of the harness was being shown. And this is good because this application is intended to be used to fabricate the harnesses, so it makes sense to only display the portion of the harness that you're working on. So as I said earlier, the the harness model product structure was maintained for the between the going from CAD to the Unity prefab, at least to the first level beneath the top level, and this was maintained so that we could get that good performance. So you can see here that the harness has about 20 or so part numbers below the top level, and each of these can be shown or hidden using this menu in the application. So if you hide all of the ones except for hide all of the harness part numbers except for the one that you're working on, you can get an experience that's much more fluid and has better performance. So now I'm going to show a video of the final prototype product, and how we tested it with the real fabrication fixture and the partially fabricated flight harness in our clean room. All right, so the conclusion of this project was we were able to find out that we needed to spend most of our time on making the models decimated and combined enough in order to work in the HoloLens, and we also had to make sure that we could manage that flow from CAD to XR, and that became a huge obstacle for what we were trying to do. We thought it would be drag and drop, and it really wasn't. And this is some of the assumptions. That the prototype kind of exposed those assumptions and those obstacles. In the end, the tactical alignment was quite good. It exceeded our expectations. Sorry, exceeded our expectations for drift and tracking and just how easy it was to complete the procedure. We did have some performance issues even with after all the decimations and combining, because these models are quite large. But we found that once you only show part of the model at a time, you could get pretty good performance, and that's the best way to do it. And it turns out that's the best way to use the application as well. So overall, the conclusion is that we have a path to a production grade application now, and it's very clear to us. So we hope to make this prototype into a full-fledged application. However, we do really want it to not only benefit electrical harness work, because it kind of blew up into this model management project, and we really want to make sure that other people can use it, because I think that would be the best way to sell this application to all of our missions and other production applications that we have. So we sort of are proposing to make this thing which I'm calling model adaptation to XR, or max reality. And this technology is basically enabling taking CAD models from our product lifecycle management and turning them into XR ready bundles. And this can be combining not just the alignment points that I was talking about, or the harnesses and the spacecraft fixtures, but also specific modules, use case specific data or mission modules for other applications, such as showing sensor data or mission data or other coordinate-based metadata. You can, anything you want. It kind of acts as the glue between the CAD model and whatever you want to show on the CAD model, which really will support a lot of aspects of SES digital engineering. And finally, some acknowledgements on this project. I'd like to send out an acknowledgement for Adam Fagan for help with the Pixie Studio decimations. And of course, I will thank the Europa Clipper mission for funding this effort, as well as JHU APL. Thank you.
All right, thank you. All right, folks, it's question and answer time. Please remember to use the question and answer function that's at the bottom of the Zoom window. We did already have one question come in through chat. Ian, do you want to repeat that one?
Yeah, sure.
New ones?
Sure. There was one question that was asked from Ken. Did you have to give up any detail going from 25 million to 500K, or did you dump some aspect that was not important to the harness? So my answer to that was there was some loss of detail, although we tried to minimize that as much as possible. You would notice, like, especially on something like the harness, there's a lot of curves, obviously, with the models of the wires and whatnot, and you will see some loss of triangle information, maybe some holes in those curves when you do some decimations. But that doesn't take away from what we're trying to accomplish there when we were trying to just see where the tie downs go, which is what was most important for this application. And we also did remove some things that were not important to the harness, like the fasteners, right? Any fasteners that were in the models needed to be completely removed and deleted, because they're not important for the AR experience.
Great, thank you. Any other questions from the audience? Give everyone a moment here. All right. Thank you again, Ian.
Thank you.
Folks, we have about 5 minutes before we're scheduled for the next talk to begin. So we're going to take a quick break, and we'll see you again at 11:45 to learn about haptics in the cockpit. Hello, everyone, and welcome back. We're getting started with our next talk. Jenni Herchek from APL will be talking about haptics in the cockpit, multimodal information exchange in XR. Let's go to the video, please.
Hi, everyone. Thank you all for coming. I'm here today to talk to you about the work Matt Bailey, Matt Pfeiffer, Reeve, and I have done for the TANG group on haptics in the cockpit. You might be wondering why I'm speaking about haptics at a mixed reality symposium. So consider this.
You're in a courtyard in a Syrian city, watching life just go on around you. Several minutes into it, there's a barrel bomb.
We have been looking deeply into VR for probably a year and a half, 2 years. We thought it was pretty compelling.
For us, the idea of Hero, what if instead of watching someone go through a thing, what if you actually got to go through that thing yourself?
In a lot of other VR, you're just using your eyes, so you're like being pulled forward just this way with your eyes. But here, all your other senses are being activated.
Over, 100 individual sounds for dialogue and dogs and various other things. We had speakers on the ground, as well as mid-level, about eye height for most people, as well as speakers above you. The computer, as it's going along, is tracking the position. It was a huge technical challenge. It was an artistic challenge. It was just interesting to work on. And now that we've gotten our feet wet, I don't think there's any turning back.
So that was an example of haptics and virtual reality coupled together. So what is haptics? Well, haptics is the acquisition of information and/or the manipulation of objects via the sense of touch. Haptics, when used with virtual reality, can have a big impact on users' sense of presence when used at the right moment. So why are we looking at using haptics in the cockpit? Well, spatial disorientation accounted for 39% of all fatal accidents between 1990 and 2000 for the Air Force. Between 1993 and 2002, spatial disorientation cost the U.S. Air Force 310 lives and 243 aircrafts, which came out to $6 billion. The U.S. Navy determined that 63% of spatial disorientation crashes were fatal. So you can see that spatial disorientation is a huge problem for pilots, and currently they rely on instruments and displays to get awareness of what is going on in the world around them. But what if we could provide haptic cues to help the pilots intuitively know more about their situation, and this could help prevent crashes. In order to do this, we investigated various haptic technologies with different levels of fidelity. This began with simple concepts like a vibrating band, shown in the lower left corner, that could just give simple alerts to the pilot. And this is expanded to more complex items like the Tesla suit, which can be seen in the lower right-hand corner. We pulled from a wide range of haptic technologies and evaluated not only what would be feasible, but what would be accepted by our end user. Some of the technologies that we looked at weren't accepted by our end user, but I thought they might spark interest for other projects that you could be working on, so I'll talk about them anyways. The first one is the ultra haptics. This uses ultrasound waves to create tactile sensations mid-air by projecting shapes and textures directly onto a user's hand. This can be seen in the upper center of my screen. This technology ended up not being great for our application because the pilots couldn't feel these sensations through the gloves that they wear when they fly. However, this prevents the ultimate sanitary surface for users, and I could see this being very popular in the age of COVID. Secondly, we were inspired by a device called the Feel Reel to consider heat and smell in the cockpit. For example, we thought, what if the pilot's chair could get hot when there was a problem with the engine? Or what if the aircraft could tell that the pilot was getting sleepy and it could pump wasabi into, like a wasabi smell into the cockpit to wake up the pilot. Although these were creative ideas, they weren't very popular with our end users, so we didn't move forward with them. The devices that were popular with our end users were the haptic device, the Haptics vest, and the Tesla suit, and I'll talk more about those in the following slides. The first one is the 6 degree of freedom haptic device. The specific device that we used was called the Phantom Desktop. And all of these devices are force feedback devices that allow the user to interact with a virtual environment. So I really wish that you could all come try this device out, but since we're virtual, I'll just ask that everyone can play along with me for a second. So find a pen. I have one here. And we're gonna pretend that this is your haptic device. So everyone take their haptic device and run it across their keyboard. Like so. And doing this, you can feel the texture of the keys. Well, that's kind of how these devices work. You can touch and feel and manipulate 3D objects in a virtual environment because the device applies force feedback back onto the user's hand. This is super cool. You can feel like if different surfaces are rough, if they're smooth, you can feel like little indentations on that. And this can really help to increase the believability of your virtual world. It makes it so you can't put your hand through walls or through the floor. And it can help suspend a user's disbelief that they're in a virtual environment. These devices are commonly used to control robots, to virtually assemble parts, or to create machine interface to help design them. So we use this device to create a virtual environment in Unity, and we put like haptic bubbles to convey information to the user. And we also allowed the user to write on the surface of the terrain. So I have a video of that here. So as you can see, I am writing on the terrain and I'm drawing a path. So this could be really great for mission planning. I've put our desired path in white here. Green shows our location that we're going to, and these red dots are kind of danger zones. So I put red vibration there in the red bubble, and also I can draw big X's that we're gonna avoid these areas. And then here I have green, like maybe that's where we're gonna start. So our users were like wowed by this technology. They thought that it was super cool, but then they were kind of split on whether this added to their experience. Many of them were concerned with the weight of the device for transport and the amount of space that it would take up in a cockpit. Also, they were worried about would they be able to do these kind of fine motor controls while they're being jostled around in the aircraft. However, others thought that being able to feel the elevation change in the terrain was really helpful for mission planning, as that information is sometimes lost in 2D mission planning. Ultimately, we thought that this device was better for mission planning outside of the cockpit because of all these reasons, and we didn't move forward with developing it more. Next, I wanted to talk to you guys about the Haptics suit and the Tesla suit. These two devices, even though they're both suits, are very different. So I'm just going to take a minute to compare and contrast them. The Haptics suit is a consumer product that's intended for gaming. It's relatively low cost at $500. This was really great for us because we could buy a couple of them, make quick prototypes out of them. It's comprised of a 4x5 grid of vibrational motors on the front and the back. The Tesla suit, on the other hand, is a high-end commercial product, and it's about as realistic as you can get. It uses 80 electrostimulation channels to make it possible to feel sensations like wind and rain. but also can make you feel like you're getting punched in the stomach. It's obviously what we didn't want to do for our situation, but it has biometrics and 10 internal motion caption sensors. So first I'm going to talk a little bit more about the Haptics tack suit. One of the problems that we identified with the pilot is maintaining awareness of the horizon line in those low visibility scenarios, like that can cause spatial disorientation, like I talked about earlier. Not having awareness of the horizon line can cause low angle drift, which leads to a crash. So as I mentioned earlier, the Haptics tack suit has a 4x5 grid of vibrational motors, which you can see in the picture on the front and the back. And our idea here was that through practice, the pilot will associate the haptic feedback from the vest with the roll of the aircraft and intuitively correct for this. So to do that, we kind of created like a hula hoop area in the vest around the center, the midline. That would be if you were stable with the horizon line. And then we prototyped several haptic feedback strategies that would show if you were rolling. So I have a demonstration of that here. So this first one was continually vibrating, and you can see as the aircraft rolls, that is reflected back in the vest. We also looked at strobing so that it wouldn't be constantly vibrating, which the user can get used to. So here now you can see kind of the strobing that is happening while the aircraft is rolling. Another problem that we identified was collision with friendly aircraft, which is a lethal scenario. So we developed this strategy to increase situational awareness for the pilot about where the friendlies are. And we call this the Haptic Wingman Tracker. And this tracker provides real-time continuous feedback of where the wingman is relative to the position to help the pilot avoid collisions. To do this, we map the relative position of the wingman to where the pilot is, and then displayed this on the 4x5 array of vibrational motors on either the front or the back of the vest. Here's a demonstration of that. Here the point is kind of what side of the aircraft the friendly is on, and the friendly is that green drone that pops in and out. And you can see as I start to move around here that the position of the friendly will change relative to where I am. And then when the elevation changes, the height of that tracker changes. So lastly, I wanted to talk to you about the Tesla suit. The Tesla suit is a top and bottom, unlike the Haptics vest, which is just a vest. The goal of the Tesla suit is to provide a complete training solution to train or rehabilitate individuals. On the left-hand side, you can see where the 80 electrostimulation sites are. Each of these sites has to be calibrated individually, so setup time of the suit is quite extensive. Our exploration of this device is still in the very early stages, but one of the things we've been particularly impressed by is the motion tracking capabilities. So I have a video to demonstrate that here. You can see as our user moves that the person in the computer also moves, and you can identify where these trackers are. They're kind of the bump outs on the suit that you can see. So I hope that you've seen how haptic feedback can help fool your senses into believing that a virtual environment is reality. And I also hope that you've learned about some of the different haptic technologies that we've tried and that exist, and that maybe you can see how these could be used to improve your project or to increase the believability of the virtual environment that you're working in. So this is an ongoing project, so I hope to be able to update you with any progress that has been made and answer any questions that you might have. Thank you so much for listening to my talk.
Thank you for that presentation video. And now for the Q&A, we have both Jenni Herchek, the narrator from the video, and also another team member, Reeve Hines, who are available to answer your questions through the Q&A interface. And I see we've got questions coming in already. Wonderful. Jenni and Reeve, take it away.
So I can start with this question. How much training use do they have prior to providing feedback? And I'm guessing that they're talking about the pilots there. So our users that gave feedback were pilots who, were currently like highly trained. However, they were new to our devices. So we only had, 10, 15 minutes with each user to get them to try the devices and then provide feedback. So we would love if we had the ability to have them take our devices out in the field and try them more. And that's some of the things that we're working on. So another question, how do you foresee any issues in the terms of universal design for the haptic technologies you used? For example, if the user was smaller or larger? Yeah, so that's definitely a problem that we saw. So the Haptics suit can be adjusted for different sizes. However, the Tesla suits come in a specific size, so you have to order them for the person that they're intended for. And we even got a suit that we thought would fit a couple of our team members. And if the suit isn't snug, then those TEMS sensors don't fit against the skin, then they can't really feel those. So the Tesla suit is definitely very person specific. And if we went forward with this, we would have to, get those individually made for each pilot. Asked what type of sensors are used for motion tracking in the Tesla suit? I'm not sure off the top of my head. Do you remember, Reeve? You're on mute.
Thanks. There are a bunch of different IMUs at, I'd say about each joint in the body. There's probably one on each side. So that's 12, 15-ish IMU locations. And when you first turn it on, you have to calibrate it. So your body's all twisted up on the screen, but you stand in a certain pose for 3 seconds and it calibrates. And I was truly impressed by the tracking. As you're all in the XR community, so you're familiar with little hand tracking things and other sort of body trackers. And the accuracy of this has really impressed me. So there's a strong feature in that. And if it's just using the IMUs for body tracking, that could also probably be a more cost-effective suit and a more of a strap-on one-size-fits-all, or a Velcro-on one-size-fits-all. Back to you, Jenni.
Yeah, and I think one of the things that we were talking about is the reason that we think the motion tracking is so good is because there's a known distance between each of the sensors, so that can help with the calculations. Can haptics include stereo sound projections to inform the user where to look? So haptics is typically considered to be like the sense of touch. So sound would be kind of outside of that realm. However, as we talked about in the video, smell was also outside of that realm, and we did consider that. So we could consider sound in the future, but that doesn't necessarily fall under our category. I think we got asked, what's the biggest use for haptics? I'm not sure exactly what is intended by that question. Where is haptics being used now, or where in the cockpit that we could see the biggest use for haptics, but we're hoping to use haptics to increase the pilot's situational awareness and kind of have a sixth sense of what is going on around them.
I'll pipe in with a couple more comments. When Jenny did the drag your pen across the keyboard demo, I think that technology is really wild, where we have a little demo of this haptic pen where you can pet a bunny in 3D space, and it really feels like you're petting the soft animal. And like then there's like a brick next to it, and you like run your the stylus across like the rough brick, and it like feels like you're like catching on all those little nicks. So I think that technology has a lot of future use cases. We couldn't quite get it to land in the cockpit like Jenny is mentioning, but that's a very interesting future one, to say the least.
Yeah, another update that I kind of had after that I recorded this is that all of our demos that I presented were linked with Unity, and we did that for all of our initial testing. However, we now have both suits running with X-Plane, so we communicate via a server to gather information from X-Plane and then use that to light up the different suits. Okay, we have another question. Do we have any special preparation to the models to enable them to be haptic ready? So if that's talking about Unity, then yes, to apply haptic feedback scripts to something in Unity, it has to be meshed. So for the terrain, we had to run it through like an asset that I downloaded, a mesh terrain editor. So that would be that would have a mesh to it, because otherwise you could just go through the terrain. So they have to be meshed objects. This question is, what is the precision in terms of contact translating to pressure through VR? I think is what they're asking with the haptic pen, like the surface roughness and material. So the device gives force feedback to your hand. So it really does feel like if you run it over a smooth surface and then you run it over a rougher surface, that you'll kind of feel that like difficulty dragging it. Like I said, I wish that we could have a live demo. Maybe we could, if you're interested, set up something outside of this that you could try the device if you're interested.
Yeah, I'll yes and that. So there's a little test sample there where you have basically an eraser that you're putting on paper. And it really does feel like you're like truly touching like a piece of paper, but you're really just holding this like haptic device that like is simulating it in VR. So that's pretty incredible.
All right,
And
follow-up comments on that about the surface roughness. How does, about giving the sensation of touching different materials, and then enthusiasm for setting up a live demo, which I'll certainly second.
Yeah, so I'm not sure that would mean very much virtually for you to just, see me using the device more than it would in that video. But if you are at APL, we can set something up offline that you can come try it out. And I can drop my email in the chat if anyone wants to follow up about any of this.
I certainly encourage anyone at APL, or if you have haptic devices available to try out at other organizations, it's a often overlooked area of XR that we tend to think of it solely in terms of the visuals or perhaps the audio, but haptics can really be a rich form of both input and output. There's a question in chat asking for a link to the haptic pen.
Yeah, so the pen that we use was the Phantom Desktop, which got bought by another company, but I can put a link to a similar device.
And we talked about this B haptic vest, which is like a 20 node grid on the front and the back of the user. And that is that was pretty easy to set up and get integrated into our work. So if you're looking for like a first test, that'd be a good one. I would say that it really is about 20 nodes in the front and back, so it's not excessively precise. And we've been trying to use like 3 nodes, like triangulate and get like a specific one.
Some more questions in the Q&A. A haptic bathing cap could be used to inform a user where to look to see a threat.
Yeah, that's definitely a possibility. The B Haptics vest, the B Haptics company also makes kind of like a plate that goes on the face that can also provide haptic feedback that goes in between your VR headset and the user's face. So that could be used. I think we veered away from anything that was kind of going to be near a pilot's head just because they're already vibrating a lot and just, you know, concerns for them. But yeah, that's definitely a possibility. And someone sent a video clip. I'm not sure if but that could be interesting. We didn't put this in the video, but in the presentation, but the Tesla suit can also be used to like mimic getting punched or shot for video gaming. And one of our teammates tried this at CES, and it's pretty crazy how like that feeling is really real. Of course, we're not trying to do that on a pilot, but there's many capabilities to the Tesla suit. And I see this question, can you feel the different skins? I'm not sure what that means exactly. But if they mean like different parts in Unity, you have to apply different textures and different feedbacks to every like mesh in Unity to get different feedback.
Oh, okay, there's clarification. Can the haptic device tell the difference in skins? So, not sure what that would mean. Skin conditions, calluses, is it in any way calibrated for the user's hand?
So Matt.
Right, it's not, yeah.
Take a look at the chat session to panelist from Matt Pfeiffer.
Yeah, so Matt Pfeiffer is also on our team and has some experience with the devices. He doesn't think that you'd be able to tell different types of skins through the device. But yes, I've seen different applications for the haptic device to be used to treat, to teach like surgical applications, so that you can feel like if you're going through skin versus if you're going through kind of muscle. So if that's what they're saying, then yeah, that's kind of a common use of the device.
Yes, and on that, I've heard of a much higher fidelity. I don't know if it costs 100K or something, where there's a robot for surgery that the surgeons have like a box that they can, this is for orthopedics, so they're grinding away bone, and they have a box that the device doesn't let them go inside of until they hold down a certain button, and they can go barely inside of it. So I think that's closer to that answer. Back to you, Jenny.
Okay, so we got one more question. How quickly could a full haptic suit be donned and ready to go now and in the future? So the Tesla suit already is ready to go if you wanted to integrate that into what you're working on. And the Haptic suit is also COTS. So those could be ready to go. If you mean a custom suit, whatever the development. Oh, how fast can you put it on? Okay, so the Haptic suit, the vest is just like putting on a coat and zipping it up. The Tesla suit is a little more complicated. It has a couple of points, like it's a more difficult to get into, and also the setup time for it is quite extensive. You have to tune each kind of sensor to each person. So there's the 80 TEMS points inside the suit, and you can change the intensity of each of those to be fit for the person. So once you set it up, it could be quickly put on, but for a first-time user, it would take some time.
All right, we've got one more question in the Q&A, and then we're going to need to wrap up this session.
Okay, the question is, for a pilot, would it be better to send the sensory information to the helmet instead of the vest? Yeah, I mean, that's certainly something that we could look at. I think we were moving away from sending anything to a pilot's head or hands that they're using for other means of communication. I don't know if Reeve or Matt has something to add about that, but.
Yeah, it's interesting they noted that as that it came up in one of our brainstormings as, hey, if the helmet is more one size fits all, and accounting for hair differences and etc., is there a better way to say, like, hey, on your left, and like to gently tap or have a little motor vibrate to give them an alert that there's something on their left?
Yeah, a lot of the feedback that we wanted to give, like we said, the horizon line was one of our first ideas, and that kind of initially led to the vest being the best way to give that type of feedback.
I think there's areas of the body that are a little bit more sensate, like the hands, but we also kind of want to stay away from the hands because they've got some jobs to do. So there's a little bit of a push-pull between where the best areas to stimulate are and where we kind of need to avoid for application reasons.
Thank you. All right, thanks to all of our presenters from the haptics presentation and from the earlier talks this morning. We will be keeping the chat and Q&A windows will still be available, but we're going to take a break on the video feed until we pick up again this afternoon, which will be at 2 o'clock, where we'll be hearing about a project named Moose. See you then. Hello, everyone. Welcome back to the afternoon session of the APL XR Symposium. Before we get started with our first talk, I'd just like to acknowledge the fabulous number of attendees that we have this year. When I looked at the registration count just now, we had 345 registered attendees. That's about 100 more than the previous XR Symposium. Of course, comparing in-person attendance to virtual is not exactly fair, but still, we're delighted to see that the online model hasn't dampened your enthusiasm for these wonderful presentations. Slightly over half the attendees are APL employees, and the rest come from industry, national labs, universities, you name it, and they represent more than a dozen countries in addition to the USA. I'd also like to encourage all of you to keep on spreading the word. Invite more of your colleagues to join us. There are still many great presentations to go. Please remember to forward them the URL to register for the symposium and not just the Zoom links, so that we can keep on counting how many of you have joined us. We appreciate your involvement. Now let's move to our first talk of the afternoon session. This talk is entitled MOOS, Mixed Reality on Orbit Operations System Environment. And the presenters are Michael Pohl, Ameera Ayodeji, Nina Cohen, and Courtney Gonzales. Let's go to the video.
Hello and welcome. Thank you for joining us. I'm Michael Pohl, the principal investigator for this effort. And today our team is going to talk to you about our mixed reality on-orbit system environment, what we've termed MOOS. MOOS is meant to be a proof of concept demonstration to help answer the question, how can you get a user in the loop to help control a spacecraft rendezvous? This is an effort that was funded through the Air and Missile Defense Sector's Innovation Initiative. It was a $10,000 3-month effort with a goal of developing and prototyping and demonstrating a next generation system that would help warfighters or government sponsors solve a very difficult problem. Our original idea was to develop a system that lets you take control of a spacecraft that attempts a rendezvous. This would be advantageous in scenarios where there is an extremely low probability of success mated system failure occurs. In these cases, a trained operator would be able to utilize our system to take manual control and complete the mission through the adversity. And this is a paradigm that already exists in other domains such as flight or autonomous driving. The biggest difference being that in a spacecraft, there's typically not a user on board, whereas in an airplane or an autonomous car, there is a safety net of having a pilot or a driver be able to take over in a stressful scenario. This is where mixed reality comes in. In this kind of environment, a user can be place shifted virtually using real-time telemetry or video, as well as a virtual mock-up of the physical environment in which they may be able to take control. Our team developed MOOS to be a first-person, a first-person user-in-the-loop control of a virtual spacecraft with a real-time physical satellite surrogate being controlled with physical hardware. What we realized, however, is that MOOS is just one example of a larger problem. More specifically, how to use mixed reality as a platform for remote or distributed system control and understanding how to interface with real-world hardware in near or real time. Let me introduce you to the rest of the team. Ameera Ayodeji is our integration and test engineer. She's going to talk to you about the hardware and software interfaces that we developed. Nina Cohen is our software developer. She'll discuss how we approach this problem and some of the critical decisions that we've made. And Courtney Gonzales is a mixed reality engineer who has been a real thought leader in this space and determining how to bring mixed reality, virtual reality concepts to the Department of Defense and to other industries. And she'll discuss some of the takeaways and lessons learned that we had from this project. Now let me turn it over to Ameera to talk about hardware.
So the overall approach to designing our system was to leverage commercial off-the-shelf products and focus our efforts on developing interfaces to integrate them. To facilitate the XR experience, which we will take a deeper look into during the software section of this presentation, we made use of the Oculus Rift virtual reality headset, coupled with an Xbox controller to translate the user desired movements of the satellite. To replicate the real-time navigation of the physical satellite, we created a CubeSat prototype that comprises of an Arduino Uno, 2 servos, and a 3D printed Cube satellite. So how does it work? Once the simulation is started, as the user begins navigating, for each user input action made with the Xbox controller, a serial message is sent out. The Arduino listens for the serial message and then translates it into a degree of motion for the desired designated servo affixed to the 3D printed model. Because of the constraints we were facing with time and budget, we had to resort to a simple communication approach. The problem we saw with the serial messaging was buffer overload that sometimes created a lag with the servo motors. This, however, leaves the door open for future development and exploration in understanding how to implement VR gestures into real-time motion of objects. Now I'll hand it over to Nina to go over the software portion of our system.
As Mike and Ameera were building the hardware, Ameera was also helping me and Courtney create the visual platform. We used Unity version 2019 2.13 F1 in order to create the environment, and we used 2 pre-created satellite assets in order to continue to build our space scene. Our first step was to learn how to move the satellite. We added the functionality to move the satellite that we are trying to dock onto the other by using keyboard inputs, such as from the keys, the arrow keys. Next, it was time to move up to using a corded Xbox controller to move the satellite. And there we used the joysticks and the A and B keys or buttons. Once we could successfully move the satellite with the Xbox controller, it was time to combine the software and hardware. We used serial messages, as Ameera mentioned, to communicate the movements to the Arduino board, which in turn controlled the servos to move the CubeSat. Now let's take a look at Moose in action. Mike?
So here's a video of Moose in action. Here we have Courtney with her headset on, controlling the system with the Xbox controller. On the right-hand side of the screen, you see the virtual world in which she's experiencing. And at the bottom of your screen, we see the physical representation of our satellite moving in concert with the virtual scene.
Our team was able to quickly prototype a mixed reality environment where the user in the loop could drive a virtual satellite to dock onto another satellite, while a physical model simultaneously moved under the user's control. The simultaneous control of both the virtual and physical models was made possible by linking the Unity software to an Arduino. We were able to put all of this together in a small $10,000 budget over 3 months. This led us to believe that other control system prototyping could easily be done in mixed reality as well. Through the use of a quick, low-cost prototyping approach like ours, some faults in mission execution and designs can quickly be identified and accounted for, thus improving mission executions in the long run. As Mike mentioned at the beginning of the presentation, we realized we were really addressing a much broader problem. Mixed reality is a prime platform for remote system control and understanding how to develop a standardized interface. This realization led us to identify the following next steps. First, we would replace our VR spacecraft with a virtual twin of the physical model we wish to control. We would also replace our focus on the on-orbit rendezvous assistance to general control system research, testing, and integration. We want to combine mixed reality technologies with a physics-based model in order to control intended objects. Some areas we have identified for further exploration into this concept include UV flight control and in-flight interceptor control. Thank you all for calling into this session. If you wish to ask more questions after the Q&A, feel free to reach out to us. For now, let's open the floor to further questions.
All right, I see we've got some questions coming in already through the Q&A interface.
Yep, I saw a couple of questions from Vaughn W. So what drove the use of Xbox versus hand controllers for something like the Valve Index? At the time, we didn't have access to a Valve Index. We were just using a what was it, Ameera? The Oculus Rift, and we had previous experience with Xbox controllers, so it was a schedule driver there. We do have plans to go beyond just the use of an Xbox controller, though. Are there standard space control protocols used? The answer to that question, no. And that's one of the things that we realized is a larger scope than we were originally taking on with our project, but is ripe for exploitation. Somebody could develop a set of standardized protocols, and that would be a huge advancement in this space for end users. And Ken, did you model latency? No, we didn't. We went into this knowing that there would be, especially with spacecraft, some sort of a latency in communications. But given the scope of our project, we went in with assuming perfect communications.
Great, thank you. Any other questions from the attendees? No? Any other comments from the team? Well, got plenty of time if there's something else you'd like to add to your presentation. Okay. All right.
I just didn't know if Mike wanted to elaborate on some of the use cases where this might go in case they were missed in the recording.
Yeah, so as we said, this started off with modeling a spacecraft rendezvous, and we realized that we could do using this technology, we could do a lot more than just that. So we think of remotely piloted aircraft, which is something that currently in the DoD space, but requires high levels of telemetry, et cetera. If you could place shift a person into a Predator drone, for example, they could have a first-person view, and it'd almost be like they're flying an airplane. You could also use this in non-DoD spaces, such as sending in a bipedal robot into a hazardous environment where a human would most likely be endangered, something like a nuclear reactor or something like that, where you would not necessarily want to send a person, or it would take a lot of effort to send a person. You could use this in something like that as well.
Looks like we've got two folks in both chat and the Q&A basically asking the same thing. What's next? What are your planned next steps? What are things you'd like to do if time and funding permit? Production deployment?
So if we could get further funding for this, we would like to do just what we were talking about, is kind of solidify what that interface and the ConOps for the interface would be for generic purposes. So you could use this in different domains, and then we would also like to start, building a bigger and better prototype. Is there sponsor interest? There is not a huge amount of sponsor interest at this time. We haven't really tried to push too hard, but one of the big challenges we see with, especially with DoD government sponsors, is there is an aversion to taking on the risk. The risk being, needing to be able to have different communication protocols in potentially classified environments.
More questions from the audience? All right, thank you, Moose team. Our next talk is scheduled for 2:30, so we'll take a break for a few minutes and see you back in 15 minutes.
Thank you.
Thank you, everybody.
Hello, everyone, and welcome back to the APL XR Symposium. Let's dive right into our next talk, which is a project called VERDE. It's collaborative design review, and the presenter is Vaughn Whisker from the Penn State Applied Research Lab.
Good afternoon. I'm Dr. Vaughn Whisker from Penn State's Applied Research Lab. First, I want to say thank you to Nick and his team at APL for hosting us at the XR Symposium. So I've been at the Applied Research Lab at Penn State for about 20 years. I'm currently the head of the Visualization Technology Department within the Synthetic Environment Applications Lab, the C-Lab. And today I'm going to talk a little bit about some work that we've been doing over the course of the last maybe 20 years, looking at design and virtual reality from concept to prototype. We've really been helped along in this process over the past 20 years by advances in technology. So we've started doing design review in about 2000, 2001 timeframe in our CAVE system. And CAVEs are large room-sized virtual reality systems. They're projection-based, and they were run originally on large clusters of SGI computers. So pictured here is an SGI Onyx 2. They're about $400,000 at the time. The CAVE altogether was about $1 million. So you can look at the economy of scale required to do design review at that point. And the interesting thing here was that we were showing 20 by 20 by 40 sized spaces at a blazing 6 frames a second with that expensive hardware. Fast forward to about 2014 when the commodity VR system started to become a thing. Oculus Rift DK2 came out and really changed the game. Our previous head mount display had been about $20,000. This one was available for about $300. You still needed a high-end workstation to run it, but that high-end workstation was no longer $400,000. It was maybe $5,000. Fast forward to today, where we have things like the Oculus Quest that don't even require a computer. You can still plug it into a high-end workstation and get the graphics, but if you are willing to make some concessions, you can run all of that tetherless, which is pretty cool. And so over the course of 20 years, we've dropped 3 orders of magnitude, and that's really changed the game as far as accessibility for this technology. How did we get here? So we started in 2001 working on a Department of Energy grant, looking at construction cost reductions in the next generation of nuclear power plants. We started by taking 3D CAD models from a couple of the different reactor vendors, running them through 3D translation software, and enabling small teams of designers to walk through that content. And it was mind-blowing at the time. We looked at design, the accessibility, maintainability, operability, human factors. We had visualized 4D construction, taking the 3D CAD data and applying a schedule element to that and watching a room be constructed around you. And that was really, really cool. Fast forward a couple of years, that work transitioned to some work for the Navy. We worked on the CVN 21 program, now CVN 78, and I'll show a quick video about that. So this is me in 2006 in a motion capture suit, standing in a virtual mock-up for the CVN 21. They had a product model at the time that was built on CATIA, and we took that product model and we were translating the CAD data into a virtual mock-up. And walking through that virtual mock-up, you could make different design decisions, if you had different design team members in the space. So we were regularly having shipbuilders come in and use our CAVE system. We were regularly translating anywhere from 40 to 100,000 CAD files using automated processes to create these virtual mock-ups. And people found value in that. So this is a behind the scenes shot of that. You can see the motion capture suit here. You can see me in the CAVE standing in the virtual mock-up, and you can see the third person view that we were able to create from that. that allowed people who weren't participating in the design review to see what it looked like to have a human interacting with the CAD data prior to construction, prior to building anything. Fast forward again to 2008, down here in the bottom center. You know, based on this work, we figured that it might be interesting to start looking at designing in 3D, having a 3D space and then designing content around you. And so we're spawning CAD models and trying to figure out different ways to connect them, but the technology wasn't quite there yet. One of the reasons that people found the virtual mockup useful or immersive design useful was that it represented a significant cost savings over traditional design review tools. And so this is one experience. This was working on the Pohl Ice Arena at Penn State, $100 million sports arena. We had the designers in early on looking at the product model, walking through and figuring out different design changes that would work better. And basically, the idea was that, you know, it's much cheaper to change the design prior to construction, of course, because then you're just paying a designer to adjust the CAD model by doing rework, breaking concrete, cutting metal, etc. So in this case, they saved approximately $475,000. Fast forward again to today, and you know, now that we have the technology, now that we have the ability to translate CAD models at scale, now that we have technology that makes the virtual design view much more accessible, we wanted to put together a new tool that was collaborative, that enabled many users to connect in the same virtual space and recreate the magic that we had doing the design reviews in the cave, where we were able to put 3 to 5 people in face-to-face. You can't really do that in the VR headset now, since it's a very individualized personal environment. And so we're looking at other ways to make those things collaborative. We wanted it to be content agnostic. We wanted to be able to take data from 3D models, from CAD, from 2D sources, and allow users to create their own environment. We wanted it to be interactive. So not only are you loading your product model up, or your model that you're interested in, and walking through it or sitting in it, but you're able to design the space around you. And then we wanted it to be iterative, to support loading of models, arranging things, saving them, and then reviewing them, and then going back and moving things around. And so the whole idea there was to be able to take an idea, move through rapid prototyping, go to demonstration, and then eventually to production. And so here we're showing some TurboSquid models that we've dropped into the mock-up here. So why do this in VR? So we believe that, you know, the 3D environment allows you to design faster because it's experiential and it's egocentric. So you're basically putting yourself in that content and designing around you. You can see how much space you have. You can feel the space. We want you to be able to sketch the design very quickly. So being able to take a combination of pre-built modules, CAD models that are loaded in, and then drawing tools to be able to sketch ideas very quickly. We want to rapidly prototype. We want to be able to build and configure a prototype from an existing catalog of parts. We want to place, rotate, and scale those parts interactively. And then we want to be able to put a human in the loop, you know, as we did with the CVN21 work. So putting a tracked user in that space, and then, you know, providing a third-person view to see what it looks like to actually live in that space. And here we have one of my engineers with some Vive trackers on, you know, his ankles, his waist, and then the controllers and the head mount. And contrast that with the suit that I was wearing for the CVN21 work that was about $20,000 and had 18 different sensors. And now, you know, with inverse kinematics, you know, you need much fewer, you know, it's a much lower investment to be able to do that. And so we want to go from idea to prototype. And so that involved developing a VR-based ecosystem that enables users to do 3D data, or to do data prep, bring in 2D and 3D content of their choice, create a session, start designing the space or the building, the cockpit, the control room around them, bring in other folks to do design review, iterate with that process. Once the design review is complete, send that back to the designers to make the changes and review again, and then move on to a prototype. And so again, trying to speed this process along. So we developed a content manager, and we found that traditionally moving content into the virtual environment was a weak link in the process. We've come up with ways to script the translation of 3D models from their native format to a visualization friendly format. But currently in our Unity 3D environment, we didn't have something that allowed us to do that. And so we developed a web-based tool to support ingest of 2D and 3D objects where you can prep, convert, tag, save, and then download that content after it's been prepared. This can be extended to support 3D CAD file ingest, things like Pixies, SAP Visual Enterprise, other CAD translation tools, looking at doing automated level of detail or decimation, because CAD files are generally pretty heavy and you don't necessarily need all of that detail to do a visual design. You need a skin, you need an accurate representation, and automated tools are allowing us to do that now. And then finally, we want to be able to export this content in other forms. So we wanted to have the ability to see the model once it's been translated to make sure that everything is consistent. We want to provide a consistent user experience. Which way is forward? What's the top? Are the length, width, and height, the scale correct? Are the units correct? And so we provided some debug to be able to do that. And then once that's been complete, you can jump into the different phases of this design and review process. And that can be 2 to 3 phases. So the first phase is looking at placement of objects and configuration, where you load up a base model, whether it's an empty room, whether it's an existing piece of equipment, whether it's in an existing location or hasn't been built yet. You can load that up. And then you bring in a set of markers, a set of preloaded content to be able to place and arrange within that environment. You can save that layout for review, and that can be done as a single user or as a collaboration between multiple users. Once that's been performed, you reload the saved data. You can bring in a different team, maybe it's the management, maybe it's the end user, maybe it's the customer, and you're able to then step through a design review using various tools such as labels, letters, numbers, notes. And so our label tool has been developed to be extensible such that from a Excel spreadsheet or a CSV file, you can create a set of primary words and modifiers, and basically using your own lexicon and design review, you can modify that and then place those labels throughout the markup. So, from that markup can be saved and then sent back to the design team, have the design team come back into the model and start addressing those design changes. And looking at how you do configuration management, how you do future design reviews. And then once that's been completed, you can then move on to a prototype where you put a human in the loop, whether you drop that into a simulation, all of these things are now possible. As I said, we wanted to make this collaborative, and based on our experience with the cave, having 3 to 5 users speaking face to face, completely naturally immersed in the 3D content was valuable. And so we wanted to recreate that with the current head mount systems. And so we made all of our applications collaborative. And so In this case, we're using an avatar to represent that each user. The avatars can be colored. They can be represented by just a head and a torso and a pair of hands, or a full body. We allow voice communication between the different users so they can speak naturally between each other. And then all of the interactions within the application are shared, such that if I spawn a model, everybody sees it. If I rotate it, everybody sees it. If I leave a note, everybody sees it. If I measure, if I draw, etc. And so all of those are interactive. The application can be deployed anywhere. We wanted to create something that would work on a LAN with no external connectivity, a wide area network, a virtual private network, or virtual private cloud. There's no outside connectivity required, no cloud requirement, no reaching back to an external server. You can run it with a client as the server or as the host, or you can run as a dedicated host, which allows you to do things like having persistent sessions. We can have a host out in the cloud where there's no GPU required. On the client side, that requires a GPU to render the 3D content. And so if you want to run that in VR, that requires the beefy VR workstation with a GeForce or a Radeon or a Quadro graphics card. We can run on the desktop as an observer or participant, no VR equipment required. Or we can run on a cloud desktop on AWS or Azure. And we can also encapsulate that as an AppStream app or a VMware Horizon-like app. Some of the features that we've developed, are allowing the models to be placed, rotated, scaled, moved, content from multiple sources, whether that's CAD, whether that's 3D design, Blender, SketchUp, 3ds Max, CAD from SolidWorks, from Pro-E, from CATIA, from Revit, as well as 2D content, whether that's user interface, whether that's, an artist's conception to maybe work off of. Those can be brought in from SketchUp or Paint or Illustrator, etc. So once that content's been brought in, you can place it within the 3D environment. You can scale it, you can rotate it. We can sketch within the environment, either freehand or sketch lines, straight lines. We can measure distances between items. We can annotate, leave a note. We can edit the object's metadata. We can take screenshots, and we can save, clear, load, and recall for iterative design. I was going to do a demonstration here, but I'll leave that to the end because of this format. But here I'm showing a number of different users immersed in the 3D environment, looking at designing a cockpit around literally just a pilot and a seat, looking at user interface design, looking at how much space is required. Again, this could be a blank room. This could be an existing piece of equipment that you're building onto. This could be a LiDAR point cloud that you want to annotate or bring a new piece of equipment into. So our lessons learned, for wider adoption, you still need a desktop client. Unfortunately, we're not at the phase where we have enough hardware out there in the field. It's not ubiquitous yet. And so you still need to offer some sort of desktop option to increase use of your tool. Working with a lot of folks in the government, they don't have the high-end systems required. And so you're looking at other alternatives to perhaps fulfill that need or that requirement. And so that would be something like the cloud desktop. Right now, providing VR hardware as part of your solution, bundling the VR headset with the application. In this application, we were looking at the Valve Index, but we also support the Vive and the Rift and any other open VR based systems. We've run into many pitfalls using user submitted data, whether it's complexity of the number of polygons, whether it's the arrangement of the nodes under the 3D model. And what that does is it makes it a challenge to load the data in, to interact with it, to keep your frame rate up, sorry, and maintain a consistent user experience with selection and highlighting and things like that. We're working on ways to maybe triage some of that through the initial ingest application. Lots of unforeseen challenges deploying on systems, on networks that you don't own. Where's the data stored? How do you write temp files? How are you going to distribute the data? What permissions are required for installation? How do you install content as well? Is that something a user can or should be able to do? Looking at collaboration, what traffic does the firewall block? So working through a lot of these different issues, as we work on deploying this application on a sponsor's network. And then determining what capabilities should be networked. So you can design an application, design a great user experience, and then try and add networking, and you're probably going to fail. Thinking about networking early on is key. Looking at how you design, families of tools, families of capabilities, to be able to network those early on is important. What are our next steps? We want to be able to close the loop. We want to be able to export the 3D content that's been the 3D design to external formats, whether it's something like STEP or IGES, one of these exchange formats, using that for the human in the loop prototype, whether that's, again, staying in the Unity ecosystem or moving back out to model-based systems engineering or other simulation tool. We want to look at how we can deploy these things wider or more widely, with the high-end desktop requirements, the VR requirements, trying to figure out how we can build some of these environments from various components, looking at how we build out the ecosystem further with data management, with data ingest, optimization, and then finally export. And with that, I'm happy to answer any questions, and I want to show a quick demo video. Here's a quick demo of the capability. Here we're loading a model from Revit. So you can load a building size model and jump into one-to-one. Maybe you don't want to look at the whole building. Maybe you want to just look at a piece of it. So here's an example of a mechanical system from that building. Or maybe you want to start from a clean slate and design around a user. So here we are with just a pilot and a... Here we're loading a previous save. Let's jump in and take a look at that. Now we'll take a look at some of the interactions. Here I've jumped into one-to-one. I can load some models from our catalog here. Top-down map, a radar, system status, moving map, or an out-the-window view. Here we'll demonstrate scaling those 2D components. Those 2D components can come from Photoshop or Paint, or they could be screenshots. Here we are collaborating with a number of members of the team. You can see that it's pretty crowded, so we can go in and hide some of those participants so they're not cluttering our view. And we can bring them back. You can see that each person can move each of the components that's already been placed. Here I'll circle this and say, hey, why don't we move this over here? After iterating on the design, we come up with a final design and look at it one more time. Maybe we'll move this over here. And with that, I'd be happy to answer any questions.
All right, thank you, Vaughn. Looks like we've got quite a few questions coming in Q&A, and unfortunately, we've only got a few minutes, so let's get right to them.
Great, so we'll start from the top. Have you been able to get it running on the Oculus Quest or any other self-contained headset system? Short answer is no. We're currently, you saw the Quest 2 in the demo. I'm running that on Quest with Oculus Link, but we haven't compiled it for any of the standalones. And I think that answers Blake's question as well. What formats have we standardized on? Really, a lot of times that's sponsor driven. You know, some of the different big programs select an ecosystem and work in it, whether it's CATIA, whether it's SolidWorks, whether it's NX. So, you know, we try and figure out the various ways to pull data out of those systems and translate it into a Unity friendly format, and, you know, so FBX, OBJ, et cetera. But those tools are getting better on the front end that do that translation at scale. How do you control, or I'm sorry, have you done any experiments with web-based clients? Again, short answer is no. You know, that opens a whole can of worms with, you know, how much memory can a browser access? You know, so a lot of these things get pretty large when you're handling dynamic data. So we haven't done that to date, but that might be a way to, again, expand the ecosystem further for additional users. We think the cloud desktop's gonna fulfill that role. How do you control authentication and authorization? Right now it's you know, simple username, but all the authorization authentication is taken care of on the workstation side. You know, we do have designs on, you know, eventually maybe supporting CAC or ECA token kind of things. But the systems that we're deploying on, you know, have the login in front. And then how do you handle disparate organizations? Looking at having basically like a virtual private cloud type arrangement for each vendor. You know, so looking at somehow segmenting the environment. In terms of tool distribution, deliver source code, government purpose licensing, or executable version. Depends on the sponsor. You know, most of the stuff is under government purpose rights. Been able to import large photogrammetry models and figure out mesh splitting, cropping. Not in this tool, but in some of our other environments, we are pulling in photogrammetry models, but we're not doing mesh splitting or cropping. A lot of that stuff would have to be done on the front end. And there are a lot of really good, there's a lot of really good work being done in the community for segmentation of those types of models that makes the simplification a lot easier. Are there any technical blockers that would stop a company from offering software and charge for cloud processing, data storage? You know, we've been doing this for a long time, and, you know, as a research organization, you know, we've always wanted the community to sort of pick up the ball and run with it. You know, you start to see these tools that have a, you know, click, go to VR button. You know, Pharaoh Scan or Pharaoh Scene, for example, has a jump to VR button. I would expect to start to see, you know, some of these CAD packages doing the same thing. You know, I guess one of the challenges is that locks you into a specific ecosystem, and we tried to, you know, take a step back and have something that was system agnostic. I think
that's it on the questions for Vaughn. I'd like to remind everyone that the chat and the Q&A will stay up throughout the afternoon webinar session. So if you have further questions, you can follow up that way, or of course, contact the speaker directly. So I think we need to move on to our next speaker now. Thank you very much, Vaughn.
Thank you. Thanks for the opportunity.
All right, our next presentation is about the next generation CIC TANG, designing the Combat Information Center of the future. The presenter is Kevin Piaskowski, and he'll be joined. I believe Kevin will be joined for the Q&A by graphic artist Katie Blythe. So let's go to the video, please.
Hi everyone, I'm Kevin Piaskowski, a software engineer and human-centered designer in the air missile defense sector here at APL. I've passionately pursued immersive reality projects and gameplay both professionally and personally during my time here at APL. And I'm excited to be able to share one of the more recent efforts I've been a part of, the Next Generation Combat Information Center TANG project. So here's a quick rundown of what I'm going to talk about. First, what is TANG? And then our team's need to pivot for this effort, how we then pivoted, and then a little bit about immersive prototyping coming to you live, a new artistic approach, followed by a bit about our TANG garage, our design week share out, our current deliverable we are building, and then the challenges and lessons learned along the way. So what is TANG? TANG stands for Tactical Advancements for the Next Generation. And we use it to refer to both our program, resourced through OPNAV N94, which is the Office of the Chief of Naval Operations, and executed through PEO IWS-5, which is the Program Executive Office of Integrated Warfare Systems. And our team, which consists of problem solvers that leverage design and systems thinking methodologies to tackle complex national security challenges. TANG has been around since about 2010, originally growing out of the submarine community, and was driven by the philosophy that we should bring the end users, specifically junior sailors, to talk directly with the engineers designing and developing the submarine systems they use every day, as well as bringing in the sponsors funding those efforts. Since then, we've grown to support over 30 projects in a variety of domains and for a variety of really tough challenges, and have over 200 people who have supported those projects as TANG team members. TANG projects can materialize in the form of problem understanding and definitions, ethnographic interviews and stakeholder maps, rapid prototyping, analysis, and sometimes all of the above. We find ourselves lucky enough to tap into all of these dimensions throughout the effort I'm going to share with you today. The project I'm focusing on sharing today is looking at far future needs, missions, and technologies for the combat system of Navy surface platforms, 20 plus years in the future. Now, this project posed a particular challenge for us as COVID hit right around the same time we were really getting started. When I say TANG leverages design thinking methodologies, a huge foundational element of that is engaging with the end users in person. We like to go interview them right where they live and work to intimately understand what environment they're doing their jobs in. Traditionally, on many of our projects, after completing all that foundational research, we hold large-scale workshops with very hands-on design thinking activities like brainstorms, building prototypes to communicate ideas for solutions using live skits, with hand-built props and drawings using craft materials like foam core and pipe cleaners. But for the first time ever in TANG history, we would have to do all of this, even the workshop, completely virtually. I'm going to play an intro video now that gives a brief overview of the project and how we started to go about adapting.
The Next Generation Combat Information Center TANG Design Week was the first ever all virtual, all unclassified workshop for the TANG program. It's part of a larger project sponsored by the Missile Defense Agency to create engagement and awareness around CIC possibilities, looking ahead to about 20 years in the future. Rear Admiral Tom Drugan kicked the week off with a visionary keynote address emphasizing the need to dream big to solve hard challenges that operators face in a world of evolving threats. We structured Design Week to unlock creativity within our research framework and despite the constraints of the virtual world we've all found ourselves living in. The first day was all about inspiration that included thought-provoking TANG talks from leaders across key subject areas. Over the next 4 days, teams brainstormed ideas and then turned them into detailed concepts before stress testing them inside science fiction style vignettes. In the end, the 4 diverse teams comprised of sailors, designers, technologists, and artists collaborated to create more than 20 postcards from the future and shared them in an immersive TANG garage to all the project stakeholders. To make it all happen in the virtual space, we used a stack of applications to enable collaboration and communication, both real-time and asynchronous.
projects
from the future and shared them in an immersive TANG garage to all the project stakeholders. To make it all happen in the virtual space, we use a stack of applications to enable collaboration and communication both real-time and asynchronously. All the while, each team's resident artists were creating live renderings in an immersive virtual reality environment, using advanced prototyping tools to bring the concepts to life. During Design Week, we broke new ground for collaboration and prototyping in a virtual workshop environment so we can solve gnarly challenges like this one for the fleet. But to get where we need to go, the workshop is just the beginning. So buckle your digital seatbelts and join us on the journey.
So as you can see, we got pretty creative. We knew we had some needs. We needed a way to share out briefs and to communicate collaboratively. We wanted a way to chat asynchronously on a number of topics at once, in small teams and as a whole group. We needed a way to brainstorm, a way to prototype, a way to blow off steam, socialize, and network, and a way to bring it all together somehow so that the less tech-savvy folks in our diverse participant group can get to it all seamlessly, and so that the tech-centric individuals aren't bored within the first 10 minutes of a 5-day event. As you saw in the video, our tech stack consisted primarily of Miro, Mattermost, and Zoom for brainstorming, chat, and meetings respectively, all brought together by a single landing website page we developed specifically for the event. We used Gather.town as our digital happy hour space and pre-recorded TANG Talk videos that were short interviews asking futurists, AI experts, combat systems engineers, and a whole plethora of experts what they saw as the future of technology in the Navy, all of which were hosted on a custom implementation of the Open Streaming Platform, or OSP. But most interesting of all for this particular symposium is the way we prototyped and the end goal. We are creating an immersive CIC experience to capture the concepts that came out of our workshop and the driving needs analysis and assessments we completed over the course of the project. So first, during Design Week, one of the coolest things we did, in my humble opinion, was enable prototyping through our live streaming platform. Artists could draw in Gravity Sketch and Tilt Brush, while our teams of warfighters and engineers described their concepts to them. We gave each team an assigned artist equipped with an Oculus Quest, and all participants could go to the landing page and see the 3D sketches being worked on live at any point during the day. Through a bit of ingenuity and experimentation, our team was able to engineer a pipeline that could take concepts generated by the artists using the Oculus through a local OBS stream over to our secure OSP TANG live stream by the way of a Chromecast rigged with the Oculus, then rendered onto our landing page as an embedded live video. All of that done in such a way that our participants can directly view the streams from our landing page with the click of a single button. Here is a quick example of one of our artists putting in a quest session during the workshop. As the teams got to virtual prototyping with this crazy 3D virtual streaming, giving artists feedback and requests live as they were drawing, the artists who had supported past TANG workshops found that they loved this methodology. The live streaming provided a method for participants to give real-time feedback to the artists, allowing for incredibly rapid evolution from early quick prototype sketches to more sophisticated models seamlessly. It pushed the artists to explore their capabilities and allow participants to still have a connection with the prototype creation process. So the question is, would participants feel disconnected from their own concepts if they couldn't prototype with foam core themselves? We were cognizant of the fact that there was this looming concern that since they were not actively making foam core prototypes, participants might feel out of control of the evolution of their own ideas. We didn't want this to lead to participants not fully invested in the process and the creation of concepts. This is a major reason why we bring the users together at this point in the TANG process. How could we recreate the value that collaboration and real-time rapid prototyping bring to the solution space? While we heard from the participants is that the ability to provide the live streaming and real-time interaction with the artists as they created the concepts helped to alleviate that disconnect and actually served as a forcing function to push their concepts even further. Emerging from Design Week, we were pleasantly surprised when we found that a lot of the concepts were much more thoroughly developed than those we saw at many of our in-person workshops. As we do, we took it one step further. We asked, how can we have the participants get a fundamental understanding of the final deliverable before we even have the concepts narrowed down that will inform that final product? That's where our TANG garage comes in. A garage is a space for daydreaming, creating, building, testing, and stress testing. This is just what this project called for. So we created the virtual TANG garage. It served a few significant purposes. One, it was a collective studio for the artists to organize the art assets as they created them throughout the week. It was a 3D presentation tool for the teams to share the story of their journey throughout Design Week. And it was almost instant gratification for the participants to see all their hard work and dedication to the week's demanding brainstorm sessions. And at its very core, it was a prototype for our final deliverable. From a development perspective, we had to get creative and figure out ways to quickly and effectively retrieve, import, and place the art team's work into Unity such that we maintain the original intent and integrity of their renderings. It's like we were our own digital moving company, all handled with care. One of our developers, Martin, wrote custom scripts to take the models generated from TiltBrush or Gravity Sketch and other platforms and automatically upload them to secure APL storage, such that the art team had to click one button once they took off their headsets to pass over their assets to the development team. From there, we were able to size and place appropriately into one of the 4 team garage spaces inside of Unity. Here's a quick video walkthrough of one of our team garages for Team Milano. The Monday following the design week, the team shared out their ideas and walkthroughs, following along as we drove a live stream view of the team's corresponding garage. Aside from the late nights and long weekend trying to pull this off, the final share out was probably one of the trickiest things to do. The live stream had about a 10 to 15 second latency, so we had to try and guess whether participants would be in the script in 10 seconds and be there to look synchronized. Oh, and we had no real rehearsal time. Despite all that, this lesson in choreography served us well, which ultimately left us with many ideas for how to do it even better in the future. Following Design Week, we re-engaged with sponsors, engineering subject matter experts, and warfighters to assess each of the resulting concepts from various technical, programmatic, and usability perspectives. And now that we're in the home stretch, we're capturing the top selected concepts that came from that assessment, as well as our project story, elements from the TANG garages, and our contextual analysis in a fully immersive Unity application. Think of it as an immersive museum that captures what we learned in the past and where we are headed. We'll be delivering this experience to a sponsor location for demonstration and future workshops. We'll also be housing an internal rig inside the RP1 APL Annex for those at the lab to see for themselves. Our deliverable setups will consist of all of the custom assets, 2D, 3D, audio, and video, generated by the TANG art team housed inside of a Unity VR application. Users will view their environment through the Vive Pro Eye and interact with it using the Valve Index controllers. They'll be able to walk through an interactive tutorial at the beginning of the experience, navigate through a tunnel that will have artifacts from our analysis and early research, move on to what we call the Exploratorium, a large exhibit room where they can view all of the concepts that came out of the design week at a high level, and finally move on to our mission-centric concept rooms to dive deeper into the most sought-after concepts from design week. At this phase, as Dave mentioned in the earlier video, this TANG project was really focused on less on providing the ultimate technical solution for the Future Combat Center and more about providing opportunities and a platform for the DoD community to align around a vision for what we want it to be so we can move forward together. A large part of this, from our perspective, was creating a way for people to feel heard and continually share their ideas even after we close out this project. One way we try to do this within our immersive experience was to provide what we hope are very natural and intuitive ways for any user to leave us feedback and their own ideas while interacting with those top selected concepts. As you'll see in the following video, which showcases one of the concept scenarios that will be part of our final VR experience, we tried to incorporate numerous avenues for the user to stay engaged while learning about the concept. While the user is navigating the space, they can at any time take a look at their wristwatch, which displays important information like a mini-map and detailed information about the concept. To help navigate through the space in a more linear fashion, we implemented an audio guide named Claire. Claire will appear throughout the space and feed you information about that concept to give context. You can also respond to Claire when she asks you various questions, as you'll see in the video. Finally, we wanted to offer multiple ways for users to provide feedback on the concepts as they walk through the experience. There are markers that you can use to annotate anywhere in the space to leave 3D notes for the team, as well as the ability to leave audio recordings throughout the space to provide feedback. This feedback is then saved off and will be available for our team to review and play back at a later time. Here is a video of one of our devs, Brandon, walking through this concept room.
These are some very cool looking displays. These are some very cool looking displays.
This project has been fun and fascinating, and I hope impactful as well, but hasn't been without its challenges and lessons learned. When we first learned that we'd be moving to a week-long virtual design event, we soul-searched in trying to find ways to interact with sponsors, stakeholders, and participants that created a sense of physical proximity without the need for physical travel. We experimented with a few tools, for example, Spatial.io, with the hopes that this may be our opportunity to host the entire design week from this platform. We quickly learned that while this technology has great potential, it wasn't quite ready for prime time, namely hosting a workshop for 50+ people, especially since the fact that majority of our participants would need to utilize the mobile non-XR version of this application. Even with the tools that we settled on as our tried and true, there were still some things to sort out. Live streaming latencies could cause confusion from time to time in what participants were seeing and what the artists were actually drawing. But overall, that served as a very successful substitute for physical prototyping. So much so that we are adding a mini room to our immersive experience where users can go and draw and manipulate objects themselves to create simple scenes and prototypes of their own. Here's a clip showcasing Brandon's work on this concept. All in all, we learned a ton and now have a great framework to build on future events like this by A, reducing the feedback loop for artists to actualize participants' concepts and ideas, B, generating a forcing function to push our talented team to explore new capabilities, and finally, allowing participants to maintain a connection with their prototype creation, the TANG team, and other participants. We suspect that even when we go back to live workshops, we'll be doing at least some of our prototyping virtually. While many of the things I talked about today aren't what may be formally defined as XR driven, it begs the question as to what really makes something immersive. Is it the technology or is it the structure of the experience that truly makes something immersive? While we did use VR to prototype and create artistic renderings, much of what made our engagement feel immersive was through creating an environment of inclusion, ripe with opportunities for open-ended discussion and feedback. To continue that discussion, I'd like to first thank you for tuning in as I shared our team's journey in designing the CIC of the future. I'd also like to give a quick shout out to the team that made all this possible. First, our sponsors and our PJMs, Lynn Regia and Dave Nobles, our art and development team, Katie Blythe, Martin Veloso, Brandon Scott, Mike Yakolev, Ben Smith, and Griff Millsap. Our analysis team, Brandon Kraft, Taylor Stedman, Alice Jackson, and Nicole Sees. The Greater TANG team, Josh Smith, Jenna Marie Hill, John Burke, and Lexi Busantis. And then also the XRCC team for helping us with some equipment needs in a pinch. I would love to answer your questions and discuss further. Thanks again.
All right, thank you, Kevin. We have about 10 minutes for questions, and it looks like a couple have already started to come in from Blake.
All right, thanks, Ari. So for Blake's first question, art tools, as I mentioned in the video, we use Gravity Sketch and Tilt Brush for the Design Week concepts. The reason why, one, was because we were on the quest and we wanted to use tools that were available there, but also it's just sort of an artistic preference. We had the team try out different applications because for the most part, they weren't really experienced in using VR for this type of thing. So it was just a matter of seeing what they were comfortable with and then in real time making a decision about what makes the most sense for what the users were trying to convey to them during the design week. So it was a mix of those two applications as well as some 2D assets they were able to sketch in real time. Unexpected gotchas. So one of them is not really appreciating the fact that some of the textures that may be rendered in things like Blender don't come through as well in Unity. So there was a lot of like, oh man, this looks nothing like what they drew. How do we like regain that capability? And so, like I said, this is over the course of a weekend, trying to then present it on Monday. It was just a lot of trial and error, getting the right shaders, right textures, that sort of thing. And then sort of tying into Brandon Scott's question here about how do you avoid future choreography demo issues? So when we were live streaming, like I said in the video, we were trying to like get ahead of what our participants who were actually driving their team's discussion, trying to get ahead of them while showing off our Unity application. Part of that is just better planning and trying to rehearse like you would for any other show or play or whatever. But I think also for choreographing things like what we're doing in our current deliverable, I think just having maybe a bit more robust of like a state machine to capture important events that are happening, to make sure that the user is paying attention to them as they come up, because you may have something interesting happening on the right, but the user is focused on the left. So how do you make sure that they're also staying in line with the choreography of the demonstration? So hopefully that answers your question.
Okay. Oh, another question about Blender and Unity.
So it was a combination of things. Like we would just try other like Awesome Shader or things that were online. Sometimes it was going back to the artists and seeing if they could change how they were rendering it out in Tilt Brush or Blender, reducing some of the complex shaders or meshes that they were using, but still trying to make sure it looks like they intended. So yeah, a lot of just kind of trial and error, case by case for each different object that they were building out. Looking at James's question. So what is your sense of the TANG community's acceptance of immersive activities? I think one of the big takeaways was that it was so nice to see what the participants were trying to convey happen in real time, and in a way that was not just a drawing. And I think it was just sort of a novelty of like live streaming like you would on Twitch, but instead doing some actual work was just a new thing for people to kind of latch onto. And then in terms of like what we're delivering now, that was sort of a natural fall on of like, okay, can I play with this now? Like, can I go put the headset on and go see it for myself? Just because they were excited to see it in Design Week, they wanted to jump in themselves as well. So I think it was an overall pretty good acceptance of trying this out for this use case. So from Amy, has any consideration been given to testing views using any of the cognitive measurement devices we saw previously? Yeah, so we're using the Vive Pro Eye, which has eye tracking, but one of the things right now is we don't have the IRBs necessary to do that. Really, we're focused on just building a quick prototype. Maybe a future effort would be then actually measuring feedback that is implicit to the user, not just what they could draw with a marker or what they could do with their voice, but like, for example, on different website analytics, you may see who is scrolling through your page or who is looking at a certain widget. Trying to recreate that in VR is possible too. Just, if they never look at the widget in the right corner, maybe that's insignificant for what we're trying to convey. So yes, we considered it. It's just sort of a constraint in time and sort of restrictions legally. Great question.
Any other questions from the attendees? Okay. Well, thank you very much, Kevin.
Awesome. Thanks, Ari. Thanks to the XR team for putting this together. Appreciate it.
We're glad you could join us. All right, folks, we have about 5 minutes before our next talk is scheduled to begin, so we'll take a short break and see you at 3:30. Welcome back, everyone, and let's get started with the final talk of this afternoon's session. This talk is titled An AR Experience on the Front Lines, Our On-Premises Vuforia Implementation. And the presenter is Phil Lindberg from APL.
Hello, and welcome to APL's 2021 XR Symposium. I'm Phil Lindberg, and I'm with the Engineering Tools and Processes team here at the Applied Physics Lab. I come here today through my work with the design engineering environment side of the world, and I believe that XR technology has the power to transform the processes by which we create hardware and systems. Today, you're going to see symposium presentations that they might look at cutting edge technology or perhaps future applications we're still dreaming of. And this presentation doesn't really fall into one of those categories. It's titled An AR Experience on the Front Lines, Our On-Premises Vuforia Implementation. And I view myself as a bit of a storyteller today, sharing the paths we followed on a journey that is still far from complete. I'm also going to note this up front. While I'm discussing some specific vendor tools, I'm not here to hype or bash any particular vendor's technology, products, or techniques. But I'm here to share what we did, why we did it this way, how we went about making it happen, and what we learned along the way, in the hope that this might help others as we all work to make these technologies a more valuable resource for our organizations. So, what did we really want to do? At a high level, I view XR as a huge enabler for the data that's created in the design engineering environments I typically support. Everything from basic CAD to analysis tool results to PLM can be leveraged using XR. In my design engineering tool world, we already have high quality 3D models, but they can be difficult to share outside of a CAD environment. Simply stated, we wanted to build an environment that would help us share design engineering data through augmented reality. We already had access to the HoloLens, which is an ideal way to handle the kind of immersive experiences we were interested in creating. And as it turns out, Vuforia does a good job supporting AR capabilities through modern cell phone and tablet devices as well. We wanted to make experiences available on as wide a range of devices as possible. One concern we had early on, most of our design data has a fair number of restrictions in how it can be shared. It's generally considered to be CUI, controlled unclassified information. This creates quite a few challenges that drove many aspects of our work. In particular, this pushed us to an on-premises solution for our AR tools. Some people look at me strangely when I say we have an on-prem solution. This means we aren't using, for example, a cloud-based solution hosted by a vendor. Our data and the servers used to process it remain on our site, controlled by our team, with more flexibility to meet internal compliance requirements and other concerns. Of course, this also means we get the challenges and work associated with creating and maintaining those services. I'll also share a quick note I've seen for ThingWorx and Vuforia on-prem solutions that maybe it's applicable to other things you might be using. The new features in a vendor's cloud or internet-based offerings are generally 1 or 2 releases ahead of their on-prem solutions. You'd like to think that the on-prem code is mostly just a neatened up form of what the vendor runs in their own servers, but that hasn't been my experience. If you are looking for a very specific feature that claims to already be released, don't presume that it's been released for the on-prem form of the product until you've confirmed that. So as I mentioned earlier, it's not my intent to advocate or denigrate any particular set of products in the XR space, but it'll be useful to know what we used for this effort. All of these tools are owned by PTC. Starting with ThingWorx Foundation, this is the software platform underlying the ThingWorx Internet of Things technology. It's the environment that lets other related software do its work together. Note that this does include the Composer application, which we use later on to define data relationships between other portions of this implementation. One quick warning, this product used to be called ThingWorx Core, and you'll still find documentation that uses this older naming. The Vuforia Experience Service is the software that allows published experiences to be viewed by supported device. It makes what you see. ThingWorx Navigate is a way to gain access to enterprise PLM data in a role-based view. This is just the sort of thing we're looking for in an XR environment. We need product data, but only the data that's relevant in a given situation. Navigate gives us a lightweight, configurable way to get the data we need. Vuforia Studio is the user-level application that allows us to incorporate CAD data into AR experiences. From my point of view, this is the authoring app where my users create the experiences they want to share that are then shared through the experience service. And finally, ThingWorx View is the actual viewing application run by the HoloLens or other supported device. So, challenges. We had a few, and I'm going to cover several of them and what we learned along the way. The first, I'm just going to generically call this security, though that actually understates the number of things we ran into and continue to run into to this day. And I'm going to start with actually the elephant in the room, the HoloLens itself, which is at the center of much of what this effort did. As one of my network security team members put it, the HoloLens is too much of a network-centric device. Well, what he meant by that was that the HoloLens, it always wants to be in the internet, it always expects various services to be available, but it doesn't have the capability to host the full security stack that my network security folks require to be part of our internal network. This created a number of challenges and still dealing with them today. And for this reason, the work I've done and the demos I share here today are actually implemented within DMZ environments, which gives us some flexibility to communicate directly with the HoloLens, but come with some other limitations we're hoping to reach beyond someday. Lesson learned. Be prepared to meet resistance when trying to incorporate new devices that don't fit in well to the existing security infrastructure, and learn how to work with the people in charge of your network to address those challenges. I include this diagram just for a moment. It comes in the ThingWorx installation manual, and I include it because it took me some time to really understand what it means. In particular, note there's a number of communication paths and port numbers involved. As you'll see in the next challenge, this caused some unexpected difficulties, and I spent a lot of time really learning what this diagram meant to me. I suspect any implementation you might run into will have some similar touchstone pieces of knowledge you really need to focus on. This was mine. Next challenge along the way, configurations. In particular, what the software configuration claims it support versus what actually works. So this story comes from my earliest work with ThingWorx and Vuforia, so I know the problem I'm discovered here is no longer a concern in current releases, but it caused quite a bit of time and effort at that time, and I include it for the lessons it taught me. Yes, there can often be a big difference between what the configuration claims can be supported and what really works. In my case, it had to do with the ThingWorx Foundation and Vuforia Experience Service, which were to both reside in the same server. Turns out the installation documentation included procedures for implementing these packages on Windows Server, Red Hat Linux, and Ubuntu Linux. During my efforts to get things working, I ended up creating environments in all three of these operating systems and discovered problems in each and every one of them. It wasn't until a deep dive meeting with some very knowledgeable support folks that I finally uncovered the truth. At that moment in time, Foundation really only wanted to run under Windows, and the Experience Service would really only work well within Red Hat. Of course, now the difficulties of getting these services that we intended to run together on the same machine. To work across two systems was an exercise left to me. Further, recall my previous comment about DMZs and network challenges. It turns out that there are VLAN, virtual LAN, port limitations in my environment when crossing operating system types. Again, something I didn't know going in. I ended up getting very familiar with the details of that ThingWorx communication diagram in the previous slide that day. Lesson learned. Pay close attention to the documentation, but recognize that some of the most important information you need may only come from a specific expert in that area. Get to know them well. Later on, when we were feeling pretty good about our ThingWorx and Vuforia work, and we're confident that we could add Navigate, the PLM communication portion, without too much trouble, but once again, we discovered important underlying details. It turns out our earlier ThingWorx Foundation implementations made use of the built-in H2 database engine. Quite honestly, it's the easiest one to install. However, Foundation supports several different underlying database implementations, and it wasn't until we added Navigate that we discovered that not all databases supported by Foundation also support integration with Navigate. This important detail wasn't readily obvious in the documentation, and we ended up having to build an entirely new environment to account for it. Lesson learned. Sometimes you'll hit stumbling blocks that simply won't be seen until the critical moment arises. Be prepared to occasionally move back and take a different path, and make sure your budget and your schedule account for that happening. It's going to happen. So let's stop talking about challenges and problems for a moment and look at some basic things we can do with this environment. First up, this is a video of me using an iPad to view an AR experience through a ThingMark of a printed circuit board design. You'll see it loading up here, and I'll let it get together here. This is a rigid flex design, so you're actually seeing two separate sections of a printed circuit board connected with a flexible section, allowing the assembly to be folded. Note how I can zoom in on any section of this board to get the view I want to see. This kind of capability is just ideal for design troubleshooting, for sharing design review information. It's a powerful technique to leverage. Next up is a video that includes some code we're actually developing from a company called TTPSC. I don't actually want to cover that work in detail here, but I want to use it to show how Navigate can be used to incorporate PLM data in an AR experience. This environment includes both a helper app, seen here emulated within Vuforia Studio, and a HoloLens app. The helper app allows me to select specific components within a design hierarchy, in this case, another demonstration drone from our hardworking interns, and generate a QR code for the HoloLens. And I get the full detail of the structure and can pick just the items I want to see. And note the fields available, that's PLM fields. We'll see those again here in a moment. And now my QR code, and off to the HoloLens. From the HoloLens, I can see the entire design, but with the components selected in the helper app highlighted in red. Note that the part details window displays the data fields supplied directly by our PLM system for this design. This demonstrates how ThingWorx Navigate can be integrated with Windchill PLM directly into an AR experience. We hope to make great use of this technique for some of our further work. And finally, can I have fun with augmented reality? Yes, you can. My group has a regular fun gathering, well, before COVID, and we decided to feature a design for a folding drone that was completed, yes, by our hardworking interns. What could be more fun than an augmented reality cake? This also had the benefit of being a memorable way to share what we were doing with augmented reality with others in our group. Yes, this is a drone that has folding arms on it for the propellers. And I'd like to finish this presentation with a story about the potential of XR to share technical data across diverse groups in actually most any setting. I had the opportunity to demonstrate some of our AR tools at a large trade show. And it was readily apparent that some parents had opted to pull their kids out of school that day to see the displays at the show. It was amazing to watch what happened when adults, some with technical backgrounds, some without, and kids got into the same shared augmented reality experience, all wearing HoloLenses, each with their own view of one of our spacecraft designs. It was plainly obvious that the small group had a nearly instant understanding of what they were seeing and what it meant. Questions and answers flowed quickly and smoothly across the group, and I could just about see light bulbs blinking above each headset. This is the kind of design environment I believe XR technologies can help create. This completes the video portion of this presentation. I'll be available to answer questions and likely tell a few more stories.
All right, thank you, Phil. I see we've got one question coming in on the Q&A already. I'll remind everyone one more time, please use the Q&A interface at the bottom of your Zoom window. And let's go ahead.
Okay, I see the first question is, what are the issues with the HoloLens and the network exactly? Well, I can't get into a ton of details in this sitting, but I will note at APL we have a large number of sponsors, and a lot of the work we do for them comes with many different rules about where data can be shared, and it means we have a very restrictive network. From my point of view, the big hassle is the HoloLens. Because it's basically a Windows device, our network people view it as just another computer and basically want the same set of network software that a laptop or desktop runs to also run in a HoloLens. The problem, of course, is the HoloLens has a very limited amount of memory and compute power, most of which is set up to run its experiences. It really doesn't have anything left over to run a large suite of security-related software. Plus, most of that software we would need doesn't actually exist in a form to run on a HoloLens anyway. So fundamentally, they want a HoloLens to look, act, and feel like a laptop. HoloLenses don't act like laptops, and I haven't found a nice way around that short of going to a DMZ and not being able to work with some of the data we might like to directly while we develop these capabilities. And if there aren't other direct questions right now, I'm going to back up to one that Devin Hahn of APL answered earlier, and I went ahead and clicked the answer live on that just because I kind of wanted to address this in a separate setting, and I realized my presentation kind of heads down the path of what Devin was talking. I will also note Devin and I shared some chats on this topic before he had to leave for a 3 o'clock East Coast meeting. So I don't believe I have Devin back in the meeting right at this moment. But it turns out we have a couple things related to him, and I'm going to quote a couple things Devin told me. What do we really need to put in place to truly do design in XR? Okay, I'm pulling from his text in your Q&A window as well as some things we shared. What hardware is really required to put in place to match my current workflows? And will I actually have an advantage in my workflow when I'm done? And do the VR tools actually offer equal capabilities? Or are they simply a tethered head-mounted device, just a viewer without real CAD creation capabilities? I have answers for none of these questions today. I will tell you, infrastructure that meets our network security needs and meets the flexibility of where we want to go with these tools, and Blake Schur's I know you're jumping up and down right now because this is a pet topic of yours. We don't have that in place yet. And I'm sure one of the reasons I bring this up this way in my presentation, it's not just an APL thing. Everybody across the industry is having this. You want these very flexible devices. You want to use them quickly. And there aren't nice, neat ways to do that yet. But we need to start at the infrastructure side of the world. We need to have a way to understand the security requirements of the world we are in today. You don't have to go too far in the news to see that there are a number of challenges right there. And I get it. My security people look at a HoloLens and they see a threat. My users look at a HoloLens and see an incredibly powerful tool. Somewhere in the middle is a place to leverage the power of that tool and still meet the security requirements in our world today. And by the way, one of the places I run into, it's one thing to set up an environment that works cool, lets you create a nice video and does a nice demo. It's another thing to set up a production-worthy environment that I can count on working while I'm on vacation. And this leans toward the infrastructure side of the world and all those details of databases and operating systems and reliable infrastructure. And I see, Vaughn, you replied while I was in the middle of my rant, and I see you're heading down some of the same pathways. Yes, how we deal with models. The big thing is, in my work, I've been used to lots of detailed 3D CAD models being readily available for quite some time. They're just available in kind of complex environments that require a fair amount of system-specific knowledge. Now we're trying to democratize it, to share it across these nice new devices that are quick and easy. The data has to change in order to leverage those systems efficiently. And yes, that includes things like how meshes work, how models get simplified. I know I've spent a fair time reviewing what we've done in-house with our Pixies implementation. And it's amazing, sometimes a very complex model looks really good after running through Pixies and is a fraction of the size. And sometimes it looks awful and it's nearly as big as the original design. All this is part of that infrastructure to make this work. From Andrew, if you had a blank slate, what would you create that would allow folks working from home? Yeah, there's a common thing today, to use AR/XR in their workflow with other coworkers and their data. Is the infrastructure problem a permission to connect to the internal network or one of needing more performance? And of course, the answer to that is yes. Both of those apply. I will note both of the demos I did in my video, I did those in my home office, no problem, through our infrastructure, DMZ with publicly accessible data. Again, the network side of the world comes into play. How am I going to get a HoloLens working at home with data that has something other than public access attached to it? We're not quite there yet. And I'm going to play on Blake because he's throwing stuff out there in the back row, the peanut gallery, we'll call it. Yeah, Blake, actually vGPUs. Further, one of the ways we're kind of looking at maybe solving this problem is, gee, can something like a FedRAMP cloud machine, which gives me some ways to connect with things like a HoloLens, that are a little more flexibly than internal networks, can we find a way to meet the security requirements in there and still give us a flexible infrastructure? And by the way, when I'm looking at things like cloud vGPU kind of machines, all of a sudden my work at home situation is vastly simplified. Thanks for bringing that up, Blake. I'm not paying you enough.
All right, do we have any more questions from the attendees? Certainly encourage everyone to continue these discussions with Phil, with your colleagues, and come up with the answers so that we can use AR and XR as flexibly and effectively at home as we do in the office, because as we all understand, we're not going to be doing it in the office anytime soon. So please solve these puzzles. All right, thank you, Phil.
Thank you, Ari, and thanks to Nick and the rest of the XR team for putting this year's symposium together. Very much appreciated.
Great. Thank you to all of our speakers, to all of our attendees. We encourage you to continue spreading the word, inviting more people to register and join us tomorrow. Now, tomorrow's session, as you're probably aware, is afternoon only. We will be beginning at 2 o'clock Eastern Time. And there has been a small update to the agenda. So I encourage you to go to the XR Symposium website and check the schedule to make sure you do not miss the talks you are most looking forward to. We're going to run a little bit past 4 o'clock to accommodate all the excellent content that we've got lined up for you. So we will see you then. See you 2 o'clock. And remember, it's a separate Zoom link for tomorrow, which you should already have in the email that provided today's link. Thank you.